Okay, so I just want to real quick before we go into today's lecture give just kind of a summary of everything that we've covered. So we've talked about affine end space, how it gives us this property of translational invariance. So the only things that like make sense are things which do not really require a preserved angle or preserved magnitude of anything. We've talked about algebraic sets in affine space, irreducible sets in the Zariski topology, and then we've motivated that an affine variety is an irreducible closed set. Um, and so then a quasi-affine variety is an open subset of this variety. And this is kind of an important thing later on because it induces a topology, because the whole space is open and the empty set is open. And so taking the quasi-affine variety as the whole space, you can induce some new topology on it. And so we talked about the reverse inclusion lemma. We talked about the ideal of the union is equal to the intersection of the ideals. We talked about radical ideals and Hilbert's Null-Stellensatz. We talked about this kind of one-to-one correspondence between algebraic sets that are irreducible and their ideals being prime ideals. And this was a really big deal. We talked about maximal ideals corresponding to irreducible closed subsets, which must be points. We defined the affine coordinate ring to be the polynomial ring quotient the ideal generated by a subset of it. We talked about the fact that it's a maximal ideal. Is that true? No, that's the residue field. That's just wrong. That's okay. If y is an affine variety, then AY is an integral domain. AY is a finitely generated K-algebra. We talked about Noetherian topologies, how dimensions of topologies correspond to dimensions of chains of ideals. Yeah, that was really the important part here. Really, this whole thing, this business about a variety having dimension n minus 1 if it has a non-constant irreducible polynomial generated zero set. But then in the next lecture, we talked about projective space and how basically we did have a well-defined 0 point, but we were really looking at things in an equivalence class on the unit circle of some length. So really maybe not the unit circle, but just the circle. Theoretically, right, it's worth considering that you could just as easily do this with a square or some other geometric shape. Because all that matters is actually the angle between essentially the two vectors. Key thing that this is not a vector space, it's projective end space. We do treat them very similarly. And here the big difference is that we're calling our polynomial ring S. And so then we talked about graded rings having this decomposition into Z modules, which we know to be finite abelian groups.
So Tim, is that a modular addition sign?
It's a direct sum. So it's like S0, S1, S dot dot dot, Sn. Yeah, so it's a Cartesian
Okay.
product basically.
Thank you. Yeah.
So the same way that we talked about like Z2 cross Z3 being isomorphic to Z6, that's kind of like what this is.
Okay,
Like
that makes
Z6.
sense.
Yeah, Z6 is a graded ring. Or like Z what's 28 times 5? Z 140 gives you
20 times
14.
5 is 100.
28 times 5. Well, whatever.
28.
Pick your favorite composite integer. It's a Z whatever is a graded ring. um, and so then Yeah. And so basically we said that graded rings have this property that their direct product is contained within, this thing. So it's like, okay, maybe if you have SD plus E as a non-abelian group, but like you could have an abelian group structure embedded in it. So like Z28 is a good example because it has Z2, Z2, Z7, but it also has the abelian group, which is Z4, Z7. Um, and so in that way, like it is a graded ring because of this containment property, but it's not necessarily equality. Um, and so, oh yeah, so the things in in projective n space are called homogeneous coordinates. And then the things in polynomial rings over graded rings in projective space are called homogeneous elements or homogeneous polynomials, meaning that they all have the same, each of the terms has the same degree. Um, and so then an ideal is a homogeneous ideal if it is the direct sum of the intersection with some elements of the graded ring. So an ideal is homogeneous if it can be generated by homogeneous elements. Sums, products, and intersections, and radical ideals of homogeneous ideals are homogeneous. To test whether a homogeneous ideal is prime, we do it the same way that we always did. Turning any ring into a graded ring, we just take each SD to be the set of all linear combinations of monomials of total weight D. And so then we can only define f and s to be a function if f is a homogeneous polynomial degree D. Really, this yields us that the formula for what our polynomials have to look like to be well defined in projective space is this kind of idea of not quite linearity because we get this to the dth power term, right? But this is kind of our way of extending distance um, out as an equivalence class. So if we homogenize by a set of coordinates, say 1, 1, 1, 1, 1, 1, 1, then any scalar value on top of those in any coordinate is going to come out as that value to the dth power. And so then we said that really functions look like this, where the function of a point is equal to 0 if and only if it's equal to 0, and it's equal to 1 if it's not. And then, yeah, we defined algebraic sets. We defined, I think we had talked about Noetherian rings previously, but basically finite generation of algebraic sets is a thing because of the Noetherian ring. Y contained in Pn if it's is an algebraic set of homogeneous elements is a topology. We can define Zariski on it. A projective variety is exactly what you would want it to be. Open subset of a projective variety is a quasi-projective variety. And then this is kind of where we talked. So we talked about the ideal of a variety in projective space, where basically the equations for this triangle really give us these roots on the unit circle. And so it gives us this implicit algebraic construction to which I say, behold, a triangle. um,
That's some cool stuff, Tim.
yeah. And so if y is an algebraic set, the homogeneous coordinate ring of y is as follows, same way we had it in affine space. So then we showed that every projective variety has an open cover of affine varieties. And what this gives us is actually like a one-to-one correspondence. And so all of this notation aside, we basically say, all right, if f is a linear homogeneous polynomial, it's a hyperplane. In particular, um, if we take the zero set of a point or of a monomial in one coordinate to be hi, then the ui's have to be the open set p to the n minus hi, which are just kind of open by definition. Projective n space is covered by these open sets. So then taking a topological morphism from the open sets to affine n space, then we basically can make this happen by deleting a dimension. And that happens precisely if we're going from ui to an. We delete the ith coordinate in projective space because projective space is dimension n plus 1, affine space is dimension n. And so phi I is a homeomorphism to an with the Zariski topology. And homeomorphism is bicontinuous bijection. So inverse images of open sets are open and images of open sets are open. That's what we mean when we say bicontinuous. And as a corollary, we get the covering. So we defined regular functions, and this is really important for today specifically. We defined regular functions at the start of 1.3. In quasi-affine varieties, we said, okay, if y is an open subset, no, if y is a quasi-affine variety, a function from the quasi-affine variety to its residue field is regular at p in the variety if there exists an open neighborhood of the quasi-affine variety with p in it, and polynomials that basically agree as a fraction to be f on the open subset. So it's basically, so an open neighborhood is just a generalization of an open set. Like it's just an open set. So can we find an open set in a quasi-affine variety where for a function f, f is equal to g over h for some non-zero h? And so then regular functions on quasi-affine varieties are regular everywhere. Regular functions, we proved this on affine space, are continuous when k is identified with a1. Quasi-projective space works the same way, except they have to be homogeneous polynomials g and h of the same degree. And this just kind of holds in keeping with everything else. And so the gluing theorem is one that I was particularly excited about. Basically, if f and g are regular on a variety x, and if f is equal g on any non-empty u, which is open in x, then f equals g everywhere. And this kind of is our first example of local to global behavior about varieties, and kind of showing how this is a very powerful tool for identifying varieties. So a variety over k is for the category of varieties, a variety over k is any of the kinds that we've talked about. Morphisms in this category look like continuous maps, where for every open set in the codomain and for every regular function on that open set in the codomain, the function over here, and this commutative diagram is from hell, but the function composition f circ the morphism from the inverse image of the open set in the codomain of the morphism going to k is regular. Or in other words, this diagram commutes. I think it's easier to view through the lens of this diagram commutes, so let's talk through that. So here we have v, and you'll note that I've numbered these. The green is the way that the morphism really works, right? To show that it commutes, right? So we go from 1 over to 2. So we go from v to phi inverse of v. And then we take this inverse map back over by phi to 2. And then we take this down by f to 3.
This is like that one we did over the summer, no?
Yeah, it's a different diagram.
Okay.
But then f circ phi actually works just fine. So phi is from x to y. So phi circ f is really just this path. That's phi circ x. Um, or phi circ f. But yeah, so this is kind of our definition of a morphism, is that this thing commutes. You can go either way. Now, bicontinuous bijections, which adhere to this, are not actually isomorphisms. We actually need some information about dimensionality to make this work. So we talked at length about how, okay, well, if you have things in different dimensionality, our definition of an isomorphism is that you have a left and right inverse, which are the same thing. But if you have different dimension in the domain and the codomain of the morphism, you can't possibly have an isomorphism. So bicontinuous bijection actually does nothing for us here. Similarly, we talked about this very important thing that we will talk about at length later on in life, called the Frobenius morphism, which basically helps us, it gives us a translational invariance to adic topologies in p-adic space. You don't need to worry about that. Like, honestly, we'll get to it when we get to it. But if you let your underlying field have characteristic p, then sending this morphism over, t to the p mod p gives you the same thing, gives you t if you have a prime p. But if p is composite, just by like the definition of our additive group structure, you don't get the same thing. And so it reduces the dimension of the codomain. And so phi isn't an isomorphism, but it is bicontinuous bijection. So then yesterday, we said, okay, let y be a variety. O of y is the ring of regular functions on that variety. And then the local ring of P on Y is the ring of equivalence classes of functions which agree near P. We'll also call this the germs of regular functions. In other words, an element of OP is a pair UF where U is open and Y containing P and F is regular on U. And two things are congruent if and only if they agree on their intersection of open subsets. And then the maximal ideal of this local ring is the set of germs of regular functions which vanish at P. And this makes a lot of sense. The general localization of something, and I leave this vague intentionally because it's kind of up to you to infer context, but the localization of something at a point is basically the set of all of the things in that thing, either divided by, if it makes sense and we have division as a well-defined thing, or modded out by P. Um, so you could do this with ideals and you would have to mod out. You could do this with an element. Maybe you would have to mod out. Maybe you would be dividing things. Depends on if you're in the field of fractions or not, etc. The function field of a variety is the exact same definition, except things don't have to contain P. So it's not the local ring in P, it's all of the functions of the variety under the same equivalence relation. So then we put together this little chart that's kind of nice. So A of y is the affine coordinate ring, S of y is the homogeneous coordinate ring, O of y is the ring of regular functions, O sub P is the local ring at P on y, K of y is the function field of y. It's a lot to keep track of. K of y is a field. We can define multiplicative inverses by restricting the open subset to remove the zero set of f. We also obtain an injective map. And so if x and y are isomorphic categories, we say that O of y, O sub p, and K of y are invariants up to isomorphism such that alpha, beta, and gamma in this commutative diagram are isomorphisms and the diagram right commutes. So for an affine variety, basically the affine coordinate ring is isomorphic to the ring of regular functions, is invariant up to isomorphism. This is not true for projective space. We had a theorem. I don't think we did anything with the theorem. You can watch the recording for that. And then, yeah, so our phi I from earlier, where we were talking about open sets and projective space giving a covering in affine space. That's an isomorphism of varieties. We talked about multiplicative subsets. This is kind of our real idea of localization, is this. And then, let's see. Yeah, so x and y as affine varieties with x isomorphic y gives us that the affine coordinate rings are isomorphic as K-algebras, and it's biconditional. So this is kind of our really important relation, and really it's that the functor is an error-reducing equivalence of categories between the category of affine varieties over K and the category of finitely generated integral domains over K. And then basically, yeah, integral closure is finitely generated. That was our big conclusion. Okay, give me one moment. I need to blow my nose because it's dusty in here, and then we will start today's lecture. Okay. So today we're talking about rational maps, and basically, as we've come to see, isomorphism is a very strong property that really doesn't hold very often. Um, and so we kind of want a better way of talking about things, just in a way that makes a little bit more sense, that's a little bit more general, because we don't want to just say, like, oh, something is a rational. Or sorry, we don't want to say, oh yeah, something is a continuous map that's bicontinuous and bijective. Like that's almost meaningless. Um, so we introduced the idea of rational maps to kind of get around this problem. So I'm going to write some hand wavy definitions of what we're going to talk about today. And then we'll just see where that goes. So a rational map between varieties is basically a map where it makes sense to have a map minus finitely many things that we don't like. And then a birational map is an isomorphism where it makes sense, minus finitely many things that we don't like. So basically, it's like an isomorphism, but not quite. But like close enough that we give it a name. And then later on, birational equivalence is having the same function field, but that's actually induced by the existence of a birational map. And so getting into some formal definitions for all of this. Um, yeah, okay, so actually the way Hartshorne says this is kind of nice. In this section, we introduce the notions of rational map and birational equivalence, which are important for the classification of varieties. A rational map is a morphism which is only defined on some open subset. Since an open subset of a variety is dense, meaning that its closure is itself, this already carries a lot of information. In this respect, algebraic geometry is more rigid than differential geometry or topology. In particular, the concept of birational equivalence is unique to algebraic geometry. And so then he starts us off with the real gluing lemma, not a definition, but this is kind of like our stronger condition. So let x and y be varieties, and let phi and psi from x to y be two morphisms of varieties. And then let u be open in x with phi restricted to u equals psi restricted to u. Then phi is psi. The morphisms are the same. And so the proof sketch, he jumps to some category theory here, which blows. But basically, we say that maybe it's just worth going through. We have time. So let y contained in projective n space for some n. And the reason why we can pick projective space is because it's covered by affine space, and then we have a direct homeomorphism between their topological spaces. So like we can do this because the open subsets have an affine open covering. So we're going to prove this for projective space, but then it's going to prove it for affine space as well. And then also let I from y to Pn be the inclusion morphism, meaning everything in y gets sent to itself in Pn. We can reduce this to y is equal to Pn because there exists some variety that does this. And then consider the product Pn cross Pn, which has structure of projective variety given by what's called the Seeger embedding. And basically, it is psi from projective R space cross projective S space to projective RS plus R plus S space by A naught through AR and then B naught through BS. Oops, psi is equal to the jth element, or sorry, the ith element times the jth element. And so this gives us a projective variety structure. This is called the Seeger. And so then the morphisms phi cross psi determine a map from a variety X to Pn cross Pn, where X is given to us. And this is because it's basically just the image of Y, or the image in Y equal to Pn cross Pn. And this is in fact a morphism, but they bump it to an exercise. And so then let delta equal the set of P cross P such that P is in Pn. So it's the set basically of the diagonal like entries, sort of. And we accordingly call this the diagonal subset of Pn cross Pn. And this is really defined by the equations xi yj equal xj yi, such that I and j are 0 through n. So we're taking the ith and jth coordinates and saying, okay, you have to be equal. And because we're working on an equivalence class of these points, it works out nicely for us. And this has to be closed because this is the same thing as saying xi minus xji is equal to 0. So it's an algebraic set. It's just like a hidden algebraic set. And so it's closed in Pn cross Pn. Well, by hypothesis, and really by construction, psi cross phi evaluated on our open subset has to be contained within the diagonal subset. But because we're working in projective space, and we're working with the open subset of a variety, U is dense in X, meaning that its closure is in X. And delta is closed. And so then for really for all of X, phi cross psi of X is contained in delta. And this is a big deal. Like, this line is huge. Because this lets us take an open subset and determine global behavior of the variety. And then, because of the construction, and Hartshorne's not super clear about this, but the construction of this is determined by the equations xi yj is equal to xj yi. This means that as elements of the diagonal subset, the coordinates and the equivalence classes of the coordinates have to be the same thing. And so then psi is equal to psi. So does this proof make sense? And is this line in yellow like clear about how important that is and how it helps?
Yeah, it
So
makes sense.
yeah, and so hold on. I just want to check something real quick because um, yeah. So basically, the idea of density is that its closure is equal to the entire set. And the reason why U is dense in X is because its closure has to be the entire set because it's irreducible. So we have to fill in everything else in the space. And so now this motivates our definition of rational maps and why we care about just one subset of a variety. So let X and Y be varieties. A rational map phi from X to Y is an equivalence class of pairs U comma phi of U, where U is a non-empty open subset of X, and 5U is a morphism phi U from U to Y. Where U comma phi U are equivalent to V comma phi V if and only if phi U is equal to phi V on U cap V. Phi is a dominant rational map if the image of phi U is dense in Y. So does this make sense? Tying it back to our definition that a rational map is a map where it makes sense on some open subset. So it's also clear that our lemma up here applies to rational maps. And a rational map is not in general a map of the set X to Y. Clearly, one can compose dominant rational maps, so we can consider the category of varieties in dominant rational maps. But that is its own category. So I'm going to say new category alert. Obc is still varieties. Morphisms are dominant rational maps. And that's because we can't just compose rational maps. We have to, the image has to be dense for us to be able to compose rational maps together. And so a birational map, a birational map phi from x to y is a rational map which admits an inverse, namely a rational map psi from y to x such that psi circ phi is equal to the identity on x, and then phi circ psi is equal to the identity on y. So this was our definition of isomorphism for morphisms of varieties. And this is just generally what works. Two varieties are birational / birational equivalent, but it's easier to say birational if there exists, if and only if there exists, a birational map between them. And then the main result of this section, and I'll just maybe call it motivation, is to say that the category of varieties and dominant rational maps is equivalent to a category of finitely generated field extensions of K with morphisms or arrows reversed. And so, yeah, this is a big deal. I think that's pretty clear. Yeah. So, we loosely say that a variety is affine if it's isomorphic to an affine variety. Which, like, yeah, that makes sense. It's just kind of funny. So, let's see, lemma. Let y contained in the affine n space be a hypersurface given by f of x1 to xn is equal to 0, and z of this. So a polynomial in one variable. Then the affine n space minus this variety is isomorphic to h in n plus 1 given by f of xn plus 1 x1 xn plus 1 xn. In particular, a minus y is affine, and its affine coordinate ring is equal to k over x1 to xn localized f. And this is, in this case, a modding out localization, not a division. Yeah. All right, so now we come to the main result of the section. Let phi from x to y be a dominant rational map. Represented by u comma phi of u. Let f in the function field of y be a rational function, maybe not necessarily regular, but rational. Represented by vf, where v is open in y, and f is regular on v. So then, since the image of the dominant rational map on U is dense in Y, phi inverse sub U of V is a non-empty open subset of X. And so F circ phi of U is a regular function on phi inverse of U evaluated at B, which gives us a rational function on X. And so this gives us a homomorphism of K algebras by previous theorem. So this gives a homomorphism of K alg from K of Y to K of X. So is it clear why this is important? We're kind of getting like miles deep into abstraction here. So it's really important that if you're ever unclear on why something matters or how this ties back to latent geometry, that you say so. Okay, taking silence as a good sign. So theorem 4.4 says for every two varieties, x and y, the above construction gives a bijection between one, a set of dominant rational maps from x to y, and the set of K-algebra homomorphisms from K of y to K of x. Um, which gives an arrow reversing equivalence of categories. And this was what we really motivated up here. And it's actually almost visual. Like, I don't even think we need to go through and prove it as long as you understand the objects that we're working with, because it's very clear that the objects have an arrow reversing map between the two categories where x gets sent to k of x and y gets sent to k of y, and then their morphisms switch arrows. Um, so I actually think that this is a quite reasonable thing um, going on here. Do you guys agree with that statement? Do you feel like we need to prove this, or is this just like latently?
I think this is good.
Okay. So then, for every two varieties, the following conditions are equivalent. So this is corollary. For every x and y, the following are equivalent. So one, x is birational to y. Two, um, there exists u open in x, v open in y, with u isomorphic to v, and then kx is isomorphic to k of y as k algebras. And all of this follows just from this last theorem, so it just kind of works. And so, as an example, every variety is birational to a hypersurface. Um, and the way that we get here is by stating a few theorems about separable algebraic field extensions, um, and actually some stuff from our summer study on Galois theory. Um, before we go into this, I think I want to give everybody a 5-minute break because I know I could use it. All right. Look through your notes so far and just kind of come back at like 8:05. Okay. All right. So we're gonna cover two in this next hour, two big examples of birational maps. So one is going to be from a variety to a hypersurface. Um, the other is going to be this thing called the blowing up of a point and then the blowing up of a variety. Um, which I think is just the funniest name ever. Um, yeah, so there's this towards showing that every variety is birational to a hypersurface. There's the primitive element theorem. If I can write. And it says let L be a finite, separable field extension of a field K. Um, then there exists alpha in L, which generates L extend K. And so this, I think, should hopefully make sense from our summer study, right? Um, and so then furthermore, um, if B1 through Bn, or beta 1 through beta n, generates L over K, and if K is infinite, then alpha is a linear combination of the generators. With Ci and K. And really, if you can accept the first statement, you can accept the second statement. It's a little outside of our scope to prove this, but it makes sense, right? Like from what we know about field theory. So then, as a definition, a field extension K over little k, and I'm trying to write that. Maybe I'll do like that. Yeah, this is so K over K is separably generated if there is a base or a transcendence base of xi's for k extend k such that k is a separable algebraic extension of little k adjoin each xi. Such a base is a separating transcendence base. So does this definition make sense? We say that this k over k is separably generated if there's this transcendence base that gets us from one thing to the other. And so then, as a theorem, if capital K extend little k is finitely and separably generated than any set of generators contains a subset which is a separating transcendence base. And this makes sense. All of this makes sense. I feel like field theory is actually pretty intuitive. And so then a follow-up theorem, and I'll actually need to look up what a perfect field is because we didn't use it except for one thing. Okay. So let me do a definition real quick. So K is a perfect field. Oh wow, that's a lot of conditions. I'm just gonna say if the characteristic of K equals 0, or K is a finite field. GF. Yeah, that works. I'm okay with that. And so then the theorem that I was gonna say is that if K is a perfect field, and in particular algebraically closed, any finitely generated field extension K extend K is separably generated. So if you recall, all of this has been, for this example, let's get this this thing. So proposition, any variety X is birational, or I guess any, hold on, of dimension R. Is birational to a hypersurface Y in PR plus 1. And since we've done all of the setting up for this proof, let's do it. So the function field K over X is a finite extension of K, as we know. And then by our above theorems, K of X is separably generated over K. So we can find a transcendent space. X1 through XR in K, such that K is a finite separable extension of K adjoin X1 through XR. So it satisfies a polynomial equation with coefficients which are rational functions in XR. And this is a big line. So it satisfies a polynomial with coefficients which are rational in x1 through xr. This yields an irreducible polynomial where f of x1 through xr comma y is equal to 0, where y is maybe the original thing. And then which admits a hypersurface in the affine r+1 space with k of a r+1 birational to x. And this is just basically by construction. And then its projective closure is y in p r+1. Meaning if we just take the equivalence classes, then we get y in p+1. So are we okay with this? Is it clear how this gives us a birational equivalence? Like if we go up to our definition, where we did it down here. A birational map is a rational map, which is an equivalence class of pairs of open subsets and things which agree on those open subsets. Well, any open subset of the function field of the affine r+1 space has to be birational minus this y-th dimension. And so since its affine variety is in dimension r, its projective variety that it covers is in dimension r+1. All right. So here we're about to do our first like really big topic. And it's an example of a birational map. And I'm gonna call it just blowing up. So as another example of a birational map, we will now construct the blowing up of a variety at a point. So of a variety at a point. This is really the main tool for resolving singularities of varieties, which we haven't talked about yet, but you guys know what singularities are. They're like cusps or spots where functions like loop over themselves, or just general jump discontinuities. You know, all of these would be considered singularities. We'll formalize it later where like if f is a polynomial, then the matrix of mixed partials has the determinant. Wherever the determinant is 0, there's a singularity at those points. And so yeah. Yeah, so first we will construct the blowing up of an at 0. So So constructing BLO at 0. So we want to consider the product of the affine n space times the projective n-1 space, which is quasi-projective. If x1 through xn are coordinates for an, and if y1 through yn are homogeneous coordinates for Pn-1, then the closed subsets are defined by polynomials in xi, yj, which are homogeneous in y. So basically, as long as our monomial terms have the same degree in y, then they yield closed subsets. So then the blowing up of an at 0 is the closed subset x of an cross Pn-1 defined by the diagonal subset. And so just recalling that this is xi minus y, or xi yj is equal to xj yi, such that ij equals 1 to n. And this gives us kind of a very nice commutative diagram where we have an injective map from x into an cross Pn-1, which projects into an. And so the picture here, this lets us study things by studying the affine variety. And kind of the picture for what this commutative diagram is doing and why we care about projecting onto an or pulling back to an cross Pn-1 is it's kind of like if you have, I'm trying to draw, well, that, there we go. So if you have, I think that's about center. If you have like a snapshot of the XY plane where like maybe it looks like that, right? And then that's 0 at the center. Then what phi does is phi is a map, and I'm going to try my best to draw this. But I will admit I am not an artist in any way, shape, or form. There's a good reason for taking the time and effort here. Where basically we can now view. Wait, that was supposed to be in a different color. This curve, um, bro, hold on. Like this, where like maybe this is 0. And so what it's doing is it's like stretching out that circle into this thing, which is the blow up. So this is the blowing up at 0. And then this is the projection in affine space. Equivalently, what we're doing is at 0, we are replacing 0 with the bundle of all of the tangent vectors to 0. And then we are identifying equivalence classes of functions entering and exiting that point by their tangent line. So you can basically think of it as if you have a singularity, you can replace it with the blowing up at the singularity by attaching like this tangent bundle thing to the point where you identify all of like the curves going through the point by the tangent line that they correspond to. And so basically in the blow up of a variety at a point, a singular point gets replaced with direction in space via an cross pn minus 1. So I kind of want to stop here because Hartshorne gets into more properties of blowing up of varieties. And I kind of feel like this is an insane amount for one lecture, especially for Garrett, because he didn't get a chance to watch the first 2 of these. And so, in the interest of making sure that we're not just like going through this to go through this, that you guys are really understanding it, just think about this. Think about kind of how this idea comes out as replacing things with this tangent bundle. Think about the idea of birationality and rational maps. So, like, basically, any variety is birational to its blowing up, is how you can think of birationality there. Because all we're doing is replacing finitely many points with this tangent bundle. And yeah. Does that work for you guys?
Yeah, that works.
Okay. Well, in that case, have a good day. I'll see you tomorrow at 7.
Yep. See you
We'll
tomorrow.
see you tonight, Tim.
Yeah. Oh, actually, yeah, I'll see you tonight at 7 for AG7 part 2.
Okay.